Welcome back everyone. Today we learn about dynamics. What is a force? A force is a push or pull. Forces are vectors, meaning they have magnitude and direction. The SI unit for force is the Newton. So, what can forces do? Forces can change the motion of objects such as its direction and magnitude of acceleration. One example is pushing a baby stroller. You can change the direction and magnitude of its motion of the stroller. A force can also change shape and size of object. Such examples includes changing shape of plasticine and changing size of a rubber band. Now let us cover the 3 laws of motion. Have you tried this before? When you pull a tablecloth quick enough, the cup of coffee remains at the same position and does not move. Why is this possible? To uncover this, we should talk about Newton's first law of motion. It states that a body continues in its state of rest or uniform motion in a straight line unless compelled by a force to do otherwise. Since the force acting on the tablecloth did not act on the cup of coffee, the cup remains on the table. To understand this, we should understand about inertia. Inertia is the resistance or reluctance to change its state of motion. All objects with mass have inertia. Imagine a bus moving on a road. When the bus suddenly brakes, you will feel a force pulling you away from your seat. With inertia, the passenger has resistance or reluctance to change its state of motion. Does a heavier object suggest that the object has a higher inertia? Yes, it does. A heavier object will be more reluctant to change its state of motion. Now let us talk about the second law of motion. It states that the net external force acting on an object is the product of its mass and its acceleration. The following definition can be summarized with this formula. F net equals ma, where F net is the net force in newtons, m is the mass in kilograms, and a is its acceleration in meter per second squared. Based on the definition, we can also say that a newton is the net force acquired to move 1 kilogram of mass with an acceleration of 1 meter per second squared. Weight of an object is a result of gravitational pull, and using F equals ma, we can use this to calculate weight, which is the product of its mass and the gravitational acceleration. On Earth we can see that 0.1 kilogram of mass is 1 newton. We can say that the weight of an object is directly proportional to an object's mass. However, is there a difference between mass and weight? Yes, there is. Mass is measure of the quantity of material in an object and affects the inertia of the object. However, weight is dependent on mass and is affected by gravitational pull. A kilogram of mass on Earth has 10 newtons, while on the Moon, it has 1.6 newtons. Hence, the mass of an object is the same, but its weight may be different. Now, let us touch the last law of motion, which states that for every action, there is an equal and opposite reaction. This suggests that when a person punches an object, the object will exert a force of same magnitude on the person, but in the opposite direction. Here are 2 other scenarios where the third law occurs. When a block is placed on the table, it exerts its weight on the table. This results in a normal force exerted by the table on the block. Both the normal force and weight in this case will be of equal magnitude. On the other hand, as you walk, your feet exert a force on the ground. This results in the ground to exert an equal but opposite force on your foot. Let us talk about frictional force. Frictional force opposes motion. They act against the motion of the object. Friction arises because surfaces are never perfectly smooth. Hence, the frictional force acting against the object is directly proportional to the force pressing on the surface. Hence, we can say that friction is equals to the product of the normal force and the coefficient of friction depending on its surface. To investigate more about forces, we have to learn how to draw force diagram. To draw a force diagram, we have to take note if the situation has the following forces: weight, which is the force acting from its center of gravity downwards towards the ground. Reaction forces in contact with surface, which is the force acting on the object as a result of contact, which in this case acts on both wheels, and hence there will be two reaction forces, denoted as R or N, acting upwards. The external forces, for example, the tension in the rope when a man pulls the cart with a rope. Friction, which opposes any motion and in this case, acts in the direction opposite of the motion of the cart and is directed on the wheels of the cart. This can be remembered by using the acronym WREF. In a force diagram, the direction of the arrow suggests the direction of the force. The length of arrow suggests the magnitude of the force. Hence, forces of the same magnitude should be drawn as the same length as shown in the diagram below with the normal force and its weight. Let us practice some force diagrams. Here is a block that lay on two beams. What would the force diagram be? Here is what the force diagram should look like. Note that the arrows for the normal force and the arrow for its weight are not the same length. In fact, each arrow denoted as N is half the length of the arrow for its weight. This is because its weight is twice the magnitude of the normal force acting on one beam. Here is another scenario. A block is moving along the floor of a rough surface. How should the diagram look like? Here is what the diagram should look like. Next, a block lays on the surface of a rough slope. How should the force diagram look like? This is what it should look like. Take note that if the net force is 0, all the net forces horizontally and vertically need to be 0. If drawn to scale, forces that sum up to a net force of 0 will form a closed shape. As seen below, the force diagram forms a closed triangle. Lastly, we have a pendulum. How should this be shown in a force diagram? Here is how it should be drawn. The vector sum of all forces are not 0. The force diagram is a snapshot of a moving object during an instance in time and hence, there is a net force during this instance. We can obtain the net force from the vector triangle as shown. We can use Newton's second law of motion to explain the motion of the object. Take note that when calculating, we need to take note of which directions produce a positive force, and which directions produces a negative force. Let us use a cart being pushed along the floor as an example. We have three cases of the motion of the cart. When the external force is more than the friction, when the external force is equal to the friction, and when the external force is less than the friction. Case 1, the object accelerates. Let's assume we have an external pushing force of 5 newtons, and a friction force of 2 newtons given the equation F equals ma, and that the net force is more than 0. The acceleration of the object is more than 0. In this case, the object accelerates when the external force is more than the frictional force. Case 2, object is stationary or at constant velocity. Now, let us consider the external force and the frictional force to be 2 newtons. This results in the forces cancelling out, and hence the object has no net force. This means that given the second law of motion, the acceleration of the object is 0, which means that the object is at rest or moving at constant velocity. This shows that the first law of motion is derived from the second law of motion. Case 3, the object remains stationary. Let us assume that the external force is now 1 newton as seen in previous scenarios. We have noticed that the external force is more than 2 newtons of friction. Hence, the maximum value of friction is 2N. But what if the external force is less than 2N? Then, the floor will exert 1 newton of friction to oppose the external force. This gives a net force of 0, and the object remains stationary. Let us try to practice drawing force diagrams. Here is a ball falling in air. Draw a force diagram of a metal ball falling in air before terminal velocity, as well as its speed and acceleration. Alright. Let us think about it. What are the forces present? They are the weight of the ball and the air resistance against the motion of the ball. Taking the downward direction as positive, the net force of the ball will be positive as well. By F equals ma, we can suggest that it will be pointed downwards. Lastly, since the ball is moving downwards, the velocity of the ball will point downward. Let us recap from kinematics. As the object falls, the weight of the object in free fall remain constant while the air resistance increase proportionally with speed. Hence, this suggests that the weight is larger than the air resistance of the ball and hence, the net force downwards will be more than zero. By Newton's second law, the acceleration of the ball will be more than zero, and hence the ball will increase in velocity. As the air resistance increases, it reaches a point where it is equivalent to its weight. This results in the net force to be zero, and according to Newton's second law, the acceleration of the ball is zero. Hence, it reaches a terminal velocity and move at constant velocity when the weight of the ball is equals to the air resistance. That's all for today. Thank you for the effort to learn with me. Stay tuned for more interesting lessons. See you next time. Bye-bye.